All right, if you're studying for the AREs, especially PPD or PDD, you know there are some topics that just seem designed to trip you up. Well, today, we're going to crack the code on two of the biggest ones, the coefficient of utilization, or CU, and the light loss factor, LLF. Let's jump right in.
So think about this for a second. You go out, you buy a brand new, super powerful light fixture. You know exactly how many lumens it puts out. But how much of that light actually makes it down to your desk where you need it? The answer, and this is key, is never 100%. And understanding why is exactly what CU and LLF are all about.
Okay, here's the mental model I want you to lock in. Imagine that between the light bulb and your work surface, there are two filters. The light has to pass through both of them to get to you. The first filter is the room itself, its shape, its colors. The second filter is, well, it's time and grime, and we have to account for both. So let's tackle that first hurdle, what we're going to call the space filter. This is where the coefficient of utilization, or CU, enters the picture. This is all about the pure physics and geometry of the space you're lighting.
So what is CU, really? Well, you can think of it as an efficiency score for your room. It's a number, always between 0 and 1, that tells you what percentage of the light from that fixture is actually doing useful work. So, if a room has a CU of, say, 0.6, that means only 60% of the light is hitting your desk. The other 40%, it's just getting lost, absorbed by the walls or the ceiling.
I love this analogy. Think of your room as a funnel for light. Is it a good funnel or a bad one? A really efficient, wide funnel that directs everything right where it needs to go? That's a room with a high CU. But what about a tall, skinny, leaky funnel that loses stuff out the sides? That's a room with a low CU.
So, what makes a good funnel versus a bad one? A few big things. First, the room shape. A low, wide room lets light get right to the work surface. That gives you a low room cavity ratio, RCR, and a high CU. It's a great funnel. But a tall, narrow room, the light has to bounce off those tall walls forever, getting lost along the way. That's a high RCR and a low CU. And of course, wall color is huge. White walls are like mirrors, bouncing light down where you want it. Dark walls literally just eat the light.
Okay, here is your big exam tip. When you're reading a question and it says something like, the client wants dark mahogany walls, ding, 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 a light bulb should go off in your head. You should immediately think dark walls mean low reflectance. Low reflectance means a lower CU. A lower CU means I'm going to need more fixtures to hit the target brightness. It's that chain of logic they're testing.
All right, so our light has successfully navigated the space. Hurdle 1 is cleared, but now it has to face its second and maybe more predictable enemy, the time and grime filter. This is where the light loss factor, or LLF, comes in. This is our reality check. LLF is also a multiplier, another number between 0 and 1. But this one accounts for everything that's going to make your lighting system dimmer over time. Because let's be real, you aren't designing for how the space looks on day 1. You're designing for how it's going to perform in year 5 or year 10. LLF is the factor that makes sure it's still bright enough way down the road.
The absolute best way to think about LLF is to picture a big, beautiful window. When it's brand new and perfectly clean, light just floods in. But what does that same window look like after a few years of dust and city grime building up? Yeah, a lot less light gets through. LLF is just us as designers calculating that layer of grime before it even happens.
And this fading, it isn't a surprise, it is totally predictable. On day 1, you're at full power, 100%. But then life happens. The lamps themselves start to age and dim. Dust settles on the fixtures. Even the walls get a little dirty, which means they don't reflect as much light. LLF is simply our tool for accounting for all of this ahead of time. So let's break down what's making our window so dirty. First, you've got lamp lumen depreciation, or LLD. That's simple. Bulbs get old, they get dimmer, even LEDs. Next is luminaire dirt depreciation, LDD, a fancy term for dust collecting on the fixture. Then there's room surface dirt depreciation, RSDD. That's when our walls get grimy and stop reflecting light well. And finally, lamp burnouts, LBF, which just accounts for the fact that some bulbs in a large group might have failed. You multiply all these little factors together to get your final LLF. Pay attention, this is another huge exam tip. You have to watch for two key phrases in a lighting question. If it asks for maintained illuminance, that is your signal. It's code for you must use the light loss factor. They want the real-world brightness after time and grime have taken their toll. But if the question asks for initial illuminance, that's the easy one. They only care about day 1, so you can just ignore LLF completely.
So now we get it. We have our two filters. We've got the space filter, CU, and we have the time and grime filter, LLF. It's time to put them together in the one formula that you absolutely have to know.
And here it is, the lumen method. It might look a little scary, but it's really just the story we've been telling this whole time. Your final brightness, the illuminance, is just the total raw power from your lamps, your lumens, first pass through the space filter, so you multiply by CU, then pass through the time and grime filter, so you multiply by LLF, and then you just spread all that useful light out over the area of the room.
Let's walk through it one last time, just as a simple process. Step 1, start with the total potential light, all the lumens. Step 2, apply the penalty for the room itself, multiply by CU. Step 3, apply the penalty for the future, multiply by LLF. What you have left is the actual, real-world, maintained light level you can expect in that space.
Okay, let's pull all this together into the final cheat sheet. This is the stuff you want to have absolutely locked in for exam day. If you're going to screenshot one thing, this is it.
Here we go, the final breakdown. CU is about spatial efficiency. It's physics and geometry. It's all about the room size, its shape, the wall colors. It's your funnel. LLF is about degradation over time. It's about maintenance, aging, and dirt. It's your dirty window. Just burn this into your brain. CU is space. LLF is time.
And look, if all that is still too much to remember, I want you to boil it all down to just these two questions. Seriously, this is it. For CU, just ask yourself, is this space good at using the light I'm putting in it? And for LLF, ask, how much will the light fade over time? If you can keep those two simple questions straight, you have mastered this concept. You are ready for the ARE. You got this. Good luck.